There's one thing that's made me think a lot, for many years in a row. One thing that most people don't bother to notice, because our intuition, that very natural feeling of understanding the world, usually works quite well in everyday life. But the problem is this: when you take that intuition outside the scope of the dinner table, the road in front of your house, or the drive to work, and apply it to the scale of the universe, it collapses instantly. And I'm telling you honestly, it doesn't just collapse, it gets mercilessly crushed by the universe. Because when you really look at physics, when you examine how time works at high speeds, when you calculate the distances between stars, when you notice the strange limits of light, you start asking a very uncomfortable question. Why do we think our intuition can help us understand the universe? When you live on Earth, a tiny planet with distances measurable in minutes or hours, intuition works fine. But when you step out into space, into a place where every scale is far beyond human experience, intuition immediately blows a fuse. It doesn't know how to handle the fact that time can flow faster or slower depending on the observer. It doesn't know how to imagine a distance so vast that light, the fastest thing we know, still takes years to cross it. And it certainly doesn't know how to deal with the reality that to accelerate an object to near the speed of light, you have to supply it with so much energy that no intuitive system was ever designed to comprehend it. Think about that. If you've never left your city, you might believe that every road in the world is roughly the same length as the trip from your house to the grocery store. But you only need one cross-continental flight to realize your intuition got it completely wrong. Now magnify that error by thousands, millions of times. That's the gap between our intuition and the reality of the universe. Before you think I'm trying to make everything seem mysterious or incomprehensible, let me be clear. I am a physicist. I believe in evidence, in mathematics. I believe in truth, even when that truth doesn't fit our familiar intuition. And that's exactly why this issue fascinates me. Because when you do the math, when you look at the laws of physics, when you try to use your intuition to explain the universe, you find that intuition is no longer a reliable tool. And if we're not willing to break it, to set it aside like a ruler that's being used in the wrong place, we'll never understand why aliens can't come here. Think about that. When intuition has been so mercilessly strangled by the universe, you and I are forced to start everything over from zero. If intuition doesn't help, we have to replace it with something else. Numbers, distances, the things nature has written across the universe over the past 13.8 billion years. Because before we can ask, why haven't aliens come here yet, we have to confront a far more important question. How big is the universe really? We often say that as if it's just casual small talk, like nice weather today. But the truth is, we don't actually grasp the number we're saying. We weren't born to understand it. None of us has neural wiring designed to process tens of thousands of light years, let alone millions or billions. But if we want to talk seriously about the possibility of alien travel, we have to cross this threshold first. So let's set intuition aside for a moment and climb with me up the cosmic scale ladder, each step making your brain feel a little smaller. Start from our cozy little home, Earth, diameter about 12,742, come on. Sounds big, but still within the imaginable range. You could circle it in a day and a half on a cruising airplane. Everything still makes sense. Now let's zoom out one more level. The solar system. Distance from Earth to the Sun is 149.6 million kilometers. Light takes 8 minutes and 20 seconds to get there. You can still measure it in seconds. Do the mental math, and intuition still tries to hang on. But the moment we move to the nearest star, Proxima Centauri, intuition immediately lets go. Proxima Centauri is 4.24 light years away, meaning light, the fastest thing nature allows, still needs more than 4 years to travel from there to here. Try sending NASA's Parker Solar Probe, the fastest spacecraft we've ever launched, reaching 692,000 kilometers per h in 2018 to get there. Result, about 6,600 years of travel. 6,600 years. And that's just the nearest star. Now zoom out a bit more. The Milky Way, the galaxy that contains our home. It's about 100,000 light years across and contains 200 to 400 billion stars. If you traveled from one side to the other at Parker Solar Probe speed, you'd need hundreds of millions of years, longer than the entire history of multicellular animals on Earth. But we're not done yet, because above the Milky Way is the local group of galaxies. Above the local group is the Laniakea supercluster, with over 100,000 galaxies. And above Laniakea is a cosmic web of structure stretching across the entire universe that no amount of chalk, blackboards, or paper could ever fully draw. This is the non-intuitive nature of the universe. You can't draw it. You can't imagine it. You can't feel it. The only thing you can do is accept it. And if you don't truly grasp this scale, every question about aliens goes off track. Before you ask, why don't they come here? Ask yourself, where are they in a map spanning tens of billions of light years? If we can answer that, the first verdict every civilization must face becomes crystal clear. Distance. So when we start talking about whether aliens could visit Earth, the first verdict any civilization faces is distance. And I don't mean far, like you have to drive a few hours to visit relatives in the next state. No, not at all. I mean distances that life itself, no matter how evolved, has no way to overcome. Cosmic distance isn't just large. It's beyond the evolutionary capability of living beings. Let's go back to the most familiar example, Proxima Centauri, the closest star to our sun. Its distance is 4.24 light years. But that number doesn't convey the true essence of the problem. You have to feel it. So try this if the solar system were a Major League Baseball field about 120 meters long. Then Proxima Centauri wouldn't be at the stadium gate. It wouldn't be in the parking lot. It wouldn't even be in the city. It would be in another state. And in that analogy, you're asking, why don't people just run from the ball field to the next state to say hi? Distance doesn't allow it. It's not merely inconvenient, it's impossible. Now back to reality and the real numbers. Parker Solar Probe, the fastest human-made object ever launched, hitting 692,000 kilometers per h in 2018, if sent straight to Proxima Centauri, would take about 6,600 years to arrive. That's a one-way trip longer than the entire history of human civilization. By the time the probe gets there, our language will likely have changed completely. National borders will be unrecognizable, and the civilization that sent it may have vanished. And the irony is, that's the nearest star. That's our close neighbor on the cosmic map. From a physics perspective, the first step of any interstellar journey is already an unbridgeable abyss. And things get worse when you realize the speed of light isn't a goal to conquer. It's the absolute limit nature imposes on anything with mass. You can't exceed it, you can't cheat it, and you certainly can't ignore it. When you accelerate an object to near light speed, the required energy rises exponentially, and its relativistic mass increases to the point where you can't supply enough energy to break through. Science fiction often talks about warp engines or hyperspace jumps, but physics doesn't write scripts to Hollywood's wishes. Nature doesn't care about our convenience. It operates by its own rules. So even if an alien civilization is thousands of years more advanced than us, they still face the exact same limits. They're blocked by the speed of light too. And if they want to shorten travel time, they'll have to supply unimaginable amounts of energy, and then deal with all the other problems: radiation, cosmic dust collisions, spacecraft structure, and most importantly, their own lifespan. But suppose they still try, and suppose they're not 4 light years away, but 4,000 light years away, but perfectly ordinary distance inside the Milky Way. Light takes 4,000 years to cross that gap. A radio signal saying hello, sent before Alexander the Great was born, would only just reach us today. And if they're 20,000 light years away, then every idea of meeting, visiting, or chatting becomes impossible. Not because they don't want to, but because distance has canceled every possibility of encounter from the start. And remember, we're still talking about distances inside the Milky Way. If they live in another galaxy, like Andromeda, 2.54 million light years away, then every notion of travel or visiting becomes meaningless. 2.54 million light years means light, the maximum speed the universe allows, must travel continuously for 2.54 million years to arrive. No civilization lives long enough to witness that journey, let alone carry it out. All of this leads to a simple but powerful conclusion. Distance alone has already slammed the door shut. Before we even talk about energy, time, biology, or information, distance stands there as an absolute wall, a verdict every civilization must accept. The universe isn't designed for civilizations to meet each other. Stars aren't placed conveniently close for popping over. There are no intergalactic highways, no shortcuts. You can't send a ship across that distance, and neither can they. Distance is the first verdict, and it's strong enough to make a visit to Earth from any civilization in the universe impossible from the very moment the idea is conceived. And this is where we face another truth of the universe, one that many people hope can be worked around. But physics isn't traffic law. You can't get an exception. If distance is the first verdict, then the second, and perhaps the cruelest, is the speed of light. And I need to make this clear right away. The speed of light isn't a goal to strive for, a number to brag about, or a milestone you can overcome with enough persistence. It's a foundational law of the universe, a law with no exceptions, no shortcuts, no priority mechanisms, and certainly no concern whether you're a low-level civilization or a high-level one with chemical engines or antimatter reactors. Let's start with something that seems simple. You push an object to make it go faster. We do this every day. You pedal harder on a bike, it speeds up. You floor the gas in a car, it accelerates. And with that intuition, you might think that if you want a spacecraft to go from 10 kilometers per s to 20 kilometers per s, then to 50 kilometers per s, then to 100 kilometers per s, you just need to push harder. But that's Earth intuition. And as I've said, intuition has no power at cosmic scales. The problem is this: the faster you push an object, the heavier it becomes. Not heavier like stepping on a scale after a big meal and seeing a few extra pounds, but heavier in the physics sense. Relativistic mass increases. Faster, heavier. Heavier needs more energy to keep accelerating. And as you approach the speed of light, the energy curve doesn't rise linearly like you might imagine with a pencil stroke. It rises vertically. A tiny step in speed requires enormous energy, hundreds, then thousands, then millions of times more than the previous step. The harder you push, the more it refuses to go faster, because the energy you're pouring in is converting into its mass. And if you try to reach the speed of light, physics demands you supply infinite energy. Not a lot, not more than a galaxy can provide. Infinite, a number no star, no supercluster, no energy source in the universe can supply. It doesn't matter if you're from Earth or an alien from a Type 3 civilization encompassing an entire galaxy. The speed of light is the final wall. You can get very close, extremely close, but you will never cross it. And once we understand this, many questions become meaningless. For example, why don't they just come faster? Because they can't. Why not build a stronger, more advanced engine? Because the stronger it is, the more relativistic mass the ship gains. and you're stuck in the infinite energy equation again. Why not use antimatter or black hole energy? Fine. You can dream about those technologies. But no matter what you use, you're still pumping energy into a massive object. And the result is always the speed of light refuses to let you pass. That's not a technical limitation. That's not a matter of engines not being powerful enough. It's the fundamental structure of space-time, written into the universe from the moment of the Big Bang, more than 13.8 billion years ago. And to help you picture it better, try a familiar image. You're pushing a car down the road. At first it's easy. You push, it moves. But then you hit an uphill slope. You push harder. It slows down. Near the top of the hill, no matter how hard you try, your speed increase is almost zero. Now imagine that hill gets exponentially steeper, and the top of the hill is the speed of light. You could push your whole life and never get over it. Effort rises to infinity. Result rises almost negligibly. And the most important thing is no one, no civilization, no intelligence, no matter how smart, can rewrite that law. There's no negotiating with the universe. No one is allowed to exceed the speed of light. And this is precisely why all interstellar travel is strangled at the root. When distances are already so vast, thousands, tens of thousands of light years, and the maximum speed any massive object can achieve is always below the speed of light, the time required to travel from point A to point B always far exceeds the lifespan of living beings, or even the lifespan of the entire civilization that sent the ship. You can shorten distances in your imagination. You can erase the inconvenience with sci-fi episodes. But in the real universe, governed by real laws, that doesn't happen. The speed of light is a giant "do not cross" sign hanging across the cosmos. Bright, proud, and uncompromising. And the interesting part, or perhaps a bit disappointing, is that any civilization must play by this rule. No exceptions. No cosmic master gets a special pass. No metaphysical technology lets you jump over this wall. Once we truly understand this, the picture of alien travel becomes very clear. They don't come here, not because they don't want to, but because the universe locked the door the moment it was born. And once we accept that the speed of light is an absolute wall, the next natural thought for many people is, okay, if we can't go through it, why not go around? That's where concepts like warp drive and wormholes enter our imagination. Hollywood loves them. Sci-fi novels love them. And even some scientific papers occasionally mention them to spark curiosity. But let's talk straight and seriously. In the style of real physics, these are not shortcuts. They are dreams without enough energy to exist. Let's start with warp drive. In 1994, physicist Miguel Alcubierre proposed an interesting idea based on Einstein's general relativity. Instead of accelerating the ship to near light speed, you could contract space in front and expand space behind. The ship doesn't really move. It rides a bubble of space-time, like a cosmic magic carpet. Nice idea, I have to admit. But the problem appears the moment you ask the simplest question. So what energy do we need to create the warp bubble? And the answer is negative energy. Not low energy, not special energy, but negative energy. Something never observed in nature at sufficient density, and according to all current theories, impossible to produce in the required amounts. Alcubierre's initial estimate required energy equivalent to the mass of the entire observable universe. Later, more optimized models reduced it to the energy equivalent of a few stars, to fly from here to there. And we're still assuming that kind of negative energy actually exists. Meaning before you can travel even a small segment of the universe, you'd have to burn something even galaxies don't produce enough of. That's why warp drive isn't a solution. It's an intellectual exercise. Beautiful, elegant, and philosophical. But it's not technology. And if warp drive is a beautiful dream, then wormholes, the Einstein-Rosen bridges, are wild dreams. Einstein and Rosen proposed the Einstein-Rosen bridge in 1935 a structure connecting 2 points in space-time via a shortcut. Imagine folding a sheet of paper in half and poking a hole to go straight from one side to the other. In mathematics, this is perfectly valid. But when you ask, are wormholes stable? The universe laughs and says no. Stable wormhole models require exotic matter. Exotic matter with negative pressure and negative energy density to prevent the throat from collapsing in less than a trillionth of a second. No exotic matter wormhole closes instantly. With exotic matter, no one has proven it exists or can be created. Moreover, to keep a wormhole a few meters wide open, long enough for a ship to pass through, you'd need more negative energy than is contained in a neutron star, where matter density reaches 10 centimeters. We're talking about requirements that go beyond current technology and beyond any resources that could possibly exist in a galaxy. In other words, the idea is beautiful, but nature doesn't sell the materials to build it. Some people still argue, maybe aliens are advanced enough to create negative energy, but the problem isn't level of technology. It's the laws of physics. You can be smarter than us, more civilized than us. You can harness the energy of stars or even black holes, but you still have to obey the limits of general relativity, energy conditions, and space-time stability. Those don't disappear when you become a Type 2 or Type 3 civilization on the Kardashev scale. And if you say, maybe they know something we don't, remember that every successful physical theory must reproduce the results of the old one. If there's a theory beyond Einstein, it still has to keep the speed of light as the limit. That's the foundation of space-time. It's like arguing you can change the law of conservation of energy by thinking really hard. No, you're just thinking hard. And one more thing I have to add. Even if we generously assume exotic matter exists, that wormholes can be stabilized, that aliens have the energy of a star in their pocket, even if all that is true, using an amount of energy equivalent to an entire galaxy, just to take a stroll through the cosmos, is still absurd. The universe isn't designed for shortcut travel, no matter how much mathematics sometimes gives us hope. Math can bend space beautifully, but physics stands next to it and says nice, but there's no budget. And that's why I often joke with my students, if you need the energy of an entire galaxy just to go for a walk, maybe you should stay home. Warp drive? Wormholes? These aren't transportation methods. They're thought experiments written in equations, as beautiful as poetry. But equations don't pay the electric bill, and they don't pump negative energy into space-time structures, so you can hop from star to star. So when you hear someone say, aliens must have figured out how to go faster than light, you can smile and reply, it doesn't matter how smart they are. They still have to play by the rules of the universe. Because, once again, this is something every civilization, even those we've never met, must accept. The speed of light is the ceiling of the universe, and neither warp drive nor wormholes have enough energy to break through that ceiling. If distance is the first wall, then time is the barbed wire wrapped around that wall, making any attempt to overcome it utterly meaningless. This is the point that many people have never thought about. Vast distances don't just make the journey long. They make the journey stretch far beyond the lifespan of the civilization that launched it. You can launch the fastest ship possible, using every technology you can dream of. But if the trip takes tens of thousands of years, or hundreds of thousands of years, then the simple question is, who will still be there to receive that visit? And this is where the paradox begins. You can have two civilizations perfectly capable of developing communication, yet they never exist at the same time. I call this the problem of asynchronous civilizations, civilizations that are out of sync. Imagine you want to send a letter to someone 20,000 light years away. You write, "Hello, we exist. We are intelligent. We want to talk." You send it, and you wait. 20,000 years later, the letter arrives. But what about the other civilization? They may have existed. They may still exist. or they may have gone extinct 19,000 years earlier. Even if they still exist, they may have developed new cultures, new technologies, new languages, and certainly no one there remembers they ever wanted to communicate with Earth. Now let's expand the example a bit. You send a letter over 20,000 years, but the recipient has moved 500,000 times. You never catch up to them, and they never catch up to you. The problem lies in a simple but cruel truth. Civilizations are not eternal entities. They have phases of emergence, growth, peak, and decline. Their existence is measured in thousands or tens of thousands of years, while the universe operates on timescales of millions or billions of years. We have existed as Homo sapiens for about 300,000 years, and technological civilization for only about 200 years. So what do you think that time frame means in a galaxy more than 13 billion years old? The chance that two intelligent civilizations exist at the same time, develop technology at the same time, look out into the universe at the same time, and search for each other simultaneously is almost zero. And that doesn't even account for travel time yet. You might say, what about time dilation? Moving near the speed of light slows time down, right? Yes. This is one of the most beautiful effects of relativity. When you approach the speed of light, time on your ship slows relative to the outside. If you travel at 0.99 c, you might experience a few years on board, while decades or centuries pass outside. But pay attention to this. Time dilation helps you, but it doesn't help the civilization at the destination. If you travel 10,000 light years at near light speed, you might feel the trip as only a few decades. Wonderful for you. But when you arrive, the civilization you wanted to meet vanished thousands of years ago. You arrive at a neighborhood where every house has been demolished, every resident has moved away, and every trace of the letter you meant to send has disappeared. All time dilation does is let you travel without dying of old age. It doesn't make the civilization on the other side extend their lifespan to wait for you. It doesn't make two historical moments overlap. It just makes you a guest who arrives 10,000 years late for the appointment. And don't forget, to get significant time dilation, you have to travel near the speed of light, which the previous section already showed is impossible due to infinite energy requirements. So time dilation, beautiful as it is mathematically, does nothing to solve the problem of two civilizations meeting. It only explains why you can survive to witness cosmic loneliness more slowly. Now look back at human history, from the civilizations of Mesopotamia, ancient Egypt, the Maya, Rome, Greece, ancient China, all lasted from a few hundred to a few thousand years, and they vanished. A high-tech civilization like ours, if lucky, might last a few thousand more years. But a few thousand years is nothing compared to a 50,000 light-year distance from one corner of the galaxy to the other. Even if a civilization on the far side of the galaxy existed in parallel with us for 10,000 years, it's like two people on opposite sides of Earth throwing stones into the ocean at the same time and hoping they hit the bottom at the same spot. The probability is near zero. When civilizations appear randomly across 13 billion years of galactic history, the chance that two can see each other, talk to each other, or send ships to visit each other at the same moment is extremely, extremely small. And that's not pessimism. That's just mathematics. Civilizations separated by thousands of light years aren't just far apart. They're out of phase in time. One civilization may have gone extinct 5,000 years before their "we exist" signal reaches Earth. Or we might send a signal out today, and the recipient, if there is one, will only receive it when they have evolved into a different form of life or disappeared entirely. Time erases every cosmic appointment faster than distance ever could. And when time has proven it can make every civilization miss each other's rhythm on scales of thousands or tens of thousands of years, we must face a more sophisticated, quieter, but no less cruel version of that same verdict: time delay. If distance makes the journey impossible, then time delay makes even a simple conversation impossible. Because in this universe, every signal, whether light, radio waves, or any advanced form of communication an alien civilization might invent, must obey the speed of light limit. There is no express mail, no superluminal messaging, no intergalactic hotline. Everything is slow, and this delay completely destroys the possibility of two-way communication. Imagine you want to start a very simple conversation. You send a hello signal to a civilization 4 light years away, a distance still considered close neighbors on the galactic map. 4 years later, the signal arrives. If they reply immediately and send back a hi, you receive that response. Another 4 years later, 8 years just to exchange a greeting. You can't call that a conversation. You can't ask, how are you? And sit there waiting 8 years to hear pretty good. And remember, that's the closest possible distance for an intelligent civilization beyond Earth. Now apply this logic to more realistic distance: 50 light years, 500 light years, 10,000 light years, perfectly ordinary distances in the Milky Way, which spans over 100,000 light years wide. You say hello, and 10,000 years later, you hear, you ask, how's life over there? And the answer arrives at a time when your civilization has vanished. Cities have eroded to dust, and Earth may have become an entirely different ecosystem. You see, even if two civilizations exist at the same time and are close enough to communicate, time delay still completely destroys any possibility of maintaining any form of dialogue. No discussion, no exchange, no feedback, no getting acquainted, no inviting each other come over. All we can send and receive are ancient postcards, delayed thousands of years from reality. But let's keep going. The problem gets worse. Time delay doesn't just interrupt conversation. It distorts information. Suppose they receive our signal today, but that signal left Earth 300 years ago, when we were still lighting rooms with candles and didn't have radio. That means they're seeing our ancient version, and if they reply immediately, we have to wait another 300 years for the answer. So what happens if, in those 300 years, we no longer exist, or we've evolved into a different form of life, or we've migrated to another planet? Time delay makes information instantly obsolete. An invitation like "where are you? We'll come visit" is meaningless when signal travel time exceeds the lifespan of any social structure. And this leads to a painful but unavoidable conclusion. No civilization can synchronize information with another on galactic scales. No two-way communication system. No negotiation. No coordination. No planning to meet. No let's meet halfway. Nothing. The universe operates on time scales so slow that every living being becomes too late to react. And if anyone asks, what about more advanced aliens? Could they create signals faster than light? The answer is, if they did that, they wouldn't just break the laws of physics. They'd break the structure of space-time itself. Einstein would flip his desk. All of physics would collapse, and the universe would descend into chaos. No, there are no exceptions. No technology can do it. No shortcuts. No miracles. And therefore, time delay is the silent destroyer of every interstellar conversation. You may have signals. You may have detection capability, but you cannot maintain contact. When information takes hundreds, thousands, or tens of thousands of years to travel from point A to point B, every idea of communication becomes an illusion. Distance makes travel impossible. Time makes meeting impossible. And as if distance, time, and delay weren't enough for the universe to declare that no, civilizations won't easily meet each other, it places one more verdict, one more sophisticated, cruel, and almost ironic: the energy verdict. If you want to know why aliens don't come to Earth, This is where the truth becomes clearest. Because even if they had the time, and even if they had a distance just close enough to attempt the trip, they still face a brutal reality. The energy cost of that trip is completely absurd. Let's start with the simplest thing. To accelerate a ship of a few hundred tons, a modest figure compared to any interstellar spacecraft, to 0.1 c, 10% the speed of light, you need more energy than the entire United States consumes in many months. And that's only 0.1 c, a speed that still takes you decades to reach the nearest star. Ramp up to 0.5 c, 50% the speed of light. Now you're facing energy equivalent to thousands of years of global energy consumption. At 0.9 c, 90% the speed of light, you need energy equivalent to the output of hundreds of billions of nuclear reactors running continuously for decades. Why do the numbers escalate so fast? This is where we confront another saboteur, the relativistic energy equation. When you accelerate a massive object, the faster it goes, the greater its relativistic mass, meaning you have to supply even more energy to keep accelerating. And as velocity gets closer to the speed of light, that energy requirement rises exponentially. A small step in velocity, a huge jump in energy demand. Too small step energy becomes absurd. The third step, you're in the realm of celestial bodies. Imagine pushing a car. At first it moves easily. Then you push it uphill. It gets harder. But eventually you hit a vertical wall. No matter how strong you are, you can't push it up. That's how energy works as you approach the speed of light. And that's just the acceleration energy. We haven't even talked about the energy to decelerate to zero when you arrive. Half the energy to speed up, half to slow down. Total doubles. And that's why the rocket equation, the fundamental equation governing rocket motion, becomes brutally harsh in interstellar space. You want to go faster, need more fuel. But fuel has mass, needs more fuel. To push the fuel ship, gets heavier, needs even more fuel. An infinite loop that makes any ship impossible to launch if you want it to go too fast. Even technologies humans often imagine, like antimatter propulsion, are no exception. Yes, antimatter has extremely high energy density. 1 gram of antimatter can release energy equivalent to 21 kilotons, like an atomic bomb. But if you want to propel an interstellar ship, you'll need tons of antimatter. The problem? We produce antimatter in accelerators at a cost of billions of dollars for a few atoms. Even in theoretical simulations, creating enough usable antimatter requires millions of times more energy input than you get out. It's like using an excavator to dig a hole, then realizing you have to burn down your entire house to run the excavator. That's not technology. That's magic. And the universe doesn't grant it. What about fusion rockets? This is a more believable dream, since we already have nuclear fusion in nature. The sun is the clearest example. But building a stable, compact, powerful fusion reactor capable of propelling an interstellar ship is something we still haven't achieved. Even if you assume a civilization could build that reactor, they still face the same problem. The required energy still exceeds any reasonable limit. You could harvest the energy of a planet or even a star, but when you have to push a ship to 0.5 c or 0.9 c, all those energy sources become tiny. And that's not even counting the energy to shield the ship from cosmic radiation, high-speed micrometeoroids that could cause explosions equivalent to bombs, and sustaining life or automated systems for thousands of years. Engine energy is only part of the story. Energy to survive the journey is far greater. All of this leads to a simple truth. No civilization can gather enough energy to travel interstellar distances at the necessary speeds. Not because they're not smart enough, not because they haven't found the right engine, but because nature has set an energy price so unreasonable that even a Type 2 civilization, one that can harness the entire energy output of its parent star, would look at the bill and say, "No, thank you." So when we ask, why don't aliens come to Earth? The answer isn't in secret engines, magical technology, or some theory hidden in a distant cave. The answer is energy, the currency the universe uses to lock every civilization inside their own galactic neighborhood. No one has enough to afford a trip that far. You can travel in imagination. You can fly in movies. But in the real world, where energy is the currency of the cosmos, every interstellar visit is such a money-losing investment that no civilization dares sign the check. Just when you think the energy problem is discouraging enough for any civilization, the universe steps up and places another verdict on the table, one more sophisticated, more cruel, and almost mocking the rocket equation. If the energy verdict is like the universe saying, "You don't have enough money to go," then the rocket equation is like it leaning in, looking into your wallet, and saying, "Oh, and even if you do have the money, you can't carry it with you." This is the battle that you, I, aliens, and every civilization that could possibly exist in the universe always lose. The rocket equation, published by Konstantin Tsiolkovsky in 1903, sounds very simple on paper. A rocket's maximum speed depends on the exhaust velocity of its engine and the mass ratio between the initial total mass, including fuel, and the final mass after fuel is burned. It seems reasonable. You want to go faster, carry more fuel, but then you hit a philosophical problem. Fuel has mass too. You carry more fuel. The ship gets heavier, needs more fuel. To push that fuel ship gets even heavier, needs even more fuel. To push the fuel you just added. The loop continues to infinity. That's when you look back at the ship and realize we're carrying a fuel tank to push a fuel tank to push another fuel tank. Exactly what Feynman would say. You're carrying fuel to transport fuel to transport fuel. And in the end, you're just transporting fuel instead of yourself. That's the rocket equation. The physical version of the harder you try, the worse everything gets. Let's try a more concrete example. Suppose you want to accelerate from 0 to just 10% the speed of light, or 0.1 c. Sounds modest. But you need to carry an enormous amount of fuel to reach that velocity. And that fuel makes the ship heavier. Then to push all that mass, you need even more fuel. The loop keeps going. By the time you finish the calculation, you realize the fuel mass is 99.999. 9% of the total ship mass, only 0.0001%, is left for the crew, equipment, instruments, and structure. And you still haven't accounted for deceleration at the destination. To stop, you have to repeat the entire fuel cycle a second time. In other words, if you want to stop, you have to carry fuel to accelerate, and fuel to decelerate, and fuel to transport both piles of fuel. This is why every real interstellar ship design looks like giant needles, with most of the structure being fuel tanks. And the actual ship is just a tiny dot at the front or back. But the problem gets even worse. The rocket equation isn't just annoying. It's a death sentence for any idea of interstellar travel using carried fuel. If you want to go fast enough to cross a few light years in reasonable time, you have to carry so much fuel that the ship becomes technically impossible. Too much mass structure can't hold energy. Demands exceed the output of a star. And if you say, what about better engines? The answer gets worse. Better engines mean higher exhaust velocity. But fuel still has mass. And the rocket equation still holds one truth. No matter how powerful the engine, you still have to carry fuel to push the fuel itself. Imagine you want to drive across the country, but your car needs to carry thousands of liters of gas for the whole trip. You fill the tank. The car gets heavier, burns more gas, needs more tank. Car gets even heavier, and eventually you have to tow a convoy of fuel trucks several kilometers long just to move a few hundred meters. That's a simple picture of the rocket equation applied to interstellar travel. And unfortunately, the universe doesn't negotiate with you. The rocket equation has no variable for more advanced technology. It's a mathematical law. It doesn't change. No one can change it. Even if aliens have antimatter engines, nuclear fusion engines, or anything beyond our imagination, they're still stuck in Tsiolkovsky's equation. The beautiful part of the story, you're not the only one losing this battle. Every civilization in the universe loses exactly the same way. No one beats the rocket equation. It's like a strict judge that no civilization can pass qualification for, no matter how impressive their application. Imagine a dialogue between you and the universe. I want to go to that star. Carry fuel. I carried it. Carry more to push that fuel. I carried it. Carry more to push the fuel that pushes the fuel. How long are we going to keep doing this? Until you realize you're just pushing fuel and not going anywhere. That's the cruel but very humorous nature of the rocket equation. It lets you fly far enough to escape Earth, visit a few planets, send probes to the edges of the solar system. But when you want to go farther, really far to other stars, it stands up, crosses its arms, and says no. And that's why the energy verdict doesn't just come from the gigantic calculations of light speed. It also comes from the absurdity of carrying fuel. This is a battle you always lose, right from the moment you haven't even started. When you think that maybe everything is just a matter of scale, that if a civilization is strong enough, advanced enough, possessing the energy of an entire star, they could overcome the barriers we're stuck behind. The universe smiles and delivers the next verdict. Even a star-level civilization would find it not worth going. On the Kardashev scale, a Type 2 civilization can harness the entire energy output of its parent star, equivalent to about 1,000 joules per second. That's an energy level far beyond anything humanity understands today. It's the kind of energy that would allow them to build a Dyson sphere, capturing every bit of light from their star to power their technology. If anyone could explore the galaxy, surely it would be a star-level civilization. So why haven't they come here? Because the cost-benefit equation is as ruthless as the laws of physics themselves. To undertake an interstellar journey spanning thousands of light years, they would have to expend an enormous amount of energy, not just to accelerate the ship, but also to protect it from cosmic radiation, repair damage from micrometeoroids, sustain biological or mechanical systems for unimaginable durations, and most importantly, ensure the trip isn't pointless by the time they arrive. Even a Type 2 civilization would realize that using a significant portion of a star's energy to send a ship out of their galactic neighborhood is simply not rational. You might think, but they have so much energy. Yes, but even if you have a massive bank account, you don't burn your entire fortune to go to the supermarket for a loaf of bread. The benefit equation isn't just about capability, it's about purpose. What is the benefit of reaching a distant star system? You don't know what's there. You don't know if it's worth the trip. And even if you arrive, thousands or tens of thousands of years later, you still don't know whether the civilization you hope to meet still exists or vanished long before you left home. Meanwhile, right in their own star system, a Type 2 civilization could do countless more appealing things: expand to every planet, build megastructures, create universe simulations, even manipulate physics in ways we can't yet imagine. Why would they spend millions of years of resources risking a trip to a distant place just to see if anyone's there, especially when the probability of meeting anyone is near zero? Suppose there is a civilization 10,000 light years away, a perfectly ordinary distance. Light takes 10,000 years to get there. A high-speed ship, even traveling at 0.1 C or 0.2 C, would still take tens of thousands of years to arrive. To do that civilization would have to sacrifice a substantial portion of their stellar energy over a long period. They could do it, but the question isn't, can they do it, but why would they want to? This isn't a technology problem, it's a motivation problem. You don't build a 500-kilometer bridge just to see what's on the other side of the river. In the universe, building that bridge is like building it with the energy of the sun. And there's one truth many people don't like to hear, but it's the inevitable conclusion. If you follow this logic, when a civilization becomes advanced enough to travel interstellar distances, it also becomes advanced enough to realize that interstellar travel isn't worth it. Type 2 civilizations aren't limited by technology. They're limited by rationality. And that rationality says, stay in your star system. This is where you have everything you need. The whole galaxy isn't a playground. That's why the energy verdict doesn't just say not capable. It says more. Even if capable, no one chooses to do it. If you need the energy of a star just to visit the neighbors, then maybe the answer isn't let's go visit them. But maybe we weren't designed to visit each other. And that's exactly when we must face the fourth verdict. One that doesn't apply to the ship, the engine, or the energy, but to the very beings hoping to make the journey, biology. Humans, like any form of life we can imagine, are not designed for interstellar travel, not because we're weak, not because our intelligence is limited, but because nature never wrote a creature capable of surviving the conditions interstellar travel demands. You might think science fiction just needs a cool suit, a state-of-the-art life support system, and a few years of training, and you can step onto the ship and travel hundreds of light years. But when viewed through the lens of physics and biology, you see an unpleasant truth. Living bodies are not designed for space, and the universe has no intention of compromising. When talking about the biological verdict, we must start with the quietest but most dangerous enemy in space, cosmic radiation. On Earth, we have an atmosphere and magnetic field that shield us, blocking most high-energy radiation from the sun, supernovae, and extreme cosmic events. But once you leave Earth, you lose all those protections. In deep space, you're exposed to high-energy protons, heavy ions, gamma rays, fast neutrons, and all kinds of other invisible bullets flying at you at terrifying speeds. A single heavy ionizing particle, smaller in diameter than a molecule, can slice through your DNA like a hot knife through butter. A few hits, and your body can repair them. But over a journey lasting decades or centuries, the accumulated DNA damage will overwhelm every cellular repair mechanism. Mutations pile up. Cancer erupts in every organ. Cells die faster than new ones form. And that's without mentioning radiation storms from stellar flares, which could kill a crew in hours without shielding as thick as meters of concrete. But the universe doesn't stop there. It continues punishing living bodies by taking away something we always take for granted, gravity. In zero-gravity environments, the body begins to disintegrate. Not in the dramatic Hollywood disaster way, but quietly, gently, yet no less cruelly. Bones lose density at 1–2% per month. Muscles atrophy from disuse. Blood vessels change. The heart weakens because it no longer has to pump blood against gravity as on Earth. The immune system declines. Vision deteriorates. Bodily fluids rush to the head, putting pressure on the optic nerves. NASA astronauts on the ISS already struggle with alarming whole body changes after just 6 months. Now imagine what happens after 6 years, 60 years, or 600 years. No life form evolved in zero gravity. No genome is adapted for such an environment. No biological mechanism is prepared to cope with this slow but certain destruction. But if radiation and gravity loss are silent killers, then cosmic dust is the explosive one. In space, Dust isn't like the harmless particles in your house. Cosmic dust consists of metal, rock, or ice grains, ranging from a few microns to millimeters. Small, yes, but when traveling at 0.1 C or 0.5 C, they carry kinetic energy equivalent to bombs. A 1 mm dust particle hitting a ship at 0.8 C would cause an explosion equivalent to many kilotons of TNT. In other words, you're like driving through a minefield where invisible mines fly at you from every direction. To protect the ship, you need armor meters thick, made of ultra-strong materials. But more armor, heavier ship, more fuel needed. The rocket equation returns and crushes your hopes. And here's the key point. Even if you solve the energy problem, you still can't protect a living being on that journey. Not just humans, not just animals, not just plants. No biological species on any planet is designed to cross thousands of light years. Biology evolved in stable environments. Our Earth provides magnetic fields, atmosphere, pressure, gravity, day-night cycles, stable chemistry, and temperature. An interstellar journey shatters all those conditions at once. A living organism needs a stable environment, like a fish needs water. Remove it from that environment, and every system in the body begins to collapse. And biology can't self-repair in cosmic conditions. A type 2 or type 3 civilization might have better technology, better drugs, better robots, even gene editing to resist radiation. But for how long can they withstand thousands of years of zero gravity, thousands of years of DNA damage, thousands of years of hibernation without cell degradation? We know even current cryosleep destroys cell membranes. What about generation ships? You'd need hundreds of generations living inside a tiny metal tube with no nature, no sunlight, no ecosystem. And you hope they maintain society, ethics, psychology, and genetics for 6,000 years. An advanced civilization isn't that naive. They know full well that keeping a biological system stable for 10 years is hard, for 100 years nearly impossible, let alone 10,000 years. Interstellar travel isn't just a physics problem, it's a biology problem. And biology loses from the starting line. Biology wasn't written for interstellar travel. Biology was written for planets, places with atmosphere, magnetic fields, gravity, stable temperatures. Biology is nature's answer to how to live well on a specific planet, not how to travel 20,000 light years and return. The universe doesn't edit your genes for you. It only cares about its own laws. And those laws say you weren't designed to leave the place you were born. Distance said no. Time said no. Energy said no. And now biology, the thing we always believed was flexible and resilient, also says no, not because we're inferior, but because nature never created a life form suited to journeys, as long as the history of its own civilization. Consider the fragility of human civilization. We've seen empires collapse, wars, population crises, natural disasters, psychological instability, cultural conflicts, all of that happening even on a vast resource-rich planet. A steel ship a few hundred meters long cannot be a stable social model for hundreds of generations. Genes will degrade from inbreeding in small groups. Social conflicts build up. New beliefs emerge. Rules change. Original goals are forgotten. Worst of all, any failure in air recycling, water, or energy systems could lead to extinction. And such failures are almost certain over thousands of years. A generation ship isn't just a biology problem. It's sociology, psychology, genetics, and engineering, all of which tend to collapse over time. But suppose we ignore humans entirely and say, let AI make the journey. Artificial intelligence isn't killed by radiation. It doesn't need air, doesn't need gravity, doesn't suffer genetic decay, doesn't rebel from fatigue. Sounds more reasonable. But AI, no matter how powerful, still lives inside machines. Machines obey physics, and physics is unforgiving. An AI ship still obeys the speed of light limit. It still needs energy to accelerate. It still faces cosmic dust with bomb-level kinetic energy on high-speed impacts. It still has to resist ionizing radiation that damages electronics. It still has to maintain systems for thousands of years without repair hands. No AI can reprogram a burned circuit. No robot can self-replace its own structure when materials age after thousands of years in deep space. And most importantly, AI cannot break the laws of physics. It can't go faster than light to shorten the trip. It can't ignore the rocket equation. It can't produce energy from nothing. Whether you send humans, robots, or AI, every ship is trapped in the same web of fundamental limits. No space-time, no energy, no materials, no biological or mechanical system can remain stable for the time required to cross interstellar distances on the scale of thousands of light years. At this point, when every escape route through biology, technology, and physics has closed one by one, we arrive at the final verdict, one more sophisticated, more abstract, but with the power to end all romantic hopes of civilizations in the universe finding each other. The verdict of information. Even if you could overcome distance, time, energy, and biology, a scenario the universe itself has tried to prevent in every way, you still face a cold fact: they don't know we exist. Information is the currency of every meeting, every conversation, every invitation, every friendship, every alliance. But in the universe, information is the hardest thing to transmit. We've been broadcasting radio signals into space since the late 19th century, when Marconi sent the first wireless signal in 1895. If you draw an imaginary sphere expanding from Earth at the speed of light, then as of today, in 2024, that sphere has a radius of only about 120 light years. A tiny radio bubble in a galaxy 100,000 light years wide. In other words, the entire history of humanity's broadcasts has reached only 1,000th of the galaxy's diameter. That means 99.99% of the galaxy has never heard a signal from Earth. We are silent to most of the universe, not because we don't speak, but because the signals haven't arrived yet. And even within that 120 light-year radius, the chance of an intelligent civilization existing at the same time as us, with technology capable of detecting our faint radio signals, is near zero. Remember that our signals weaken rapidly as they spread, following the inverse square law of distance. What we broadcast in 1950, by the time it travels a few dozen light years, is already so weak it's nearly indistinguishable from cosmic background noise. Civilizations wanting to detect us would need receivers with unimaginable sensitivity, or they would have to accidentally look exactly at Earth at the exact moment we were broadcasting strongly, on frequencies they could measure. Those conditions combined create a probability near zero. But the information verdict doesn't stop at whether they receive our signals. It also applies to how they observe us. If a civilization 1,000 light years away is looking toward us with telescopes far more advanced than anything we've dreamed of, they would see Earth from the year 1024, when we were still in the Middle Ages. They wouldn't see the internet, satellites, or cities glowing at night. They would see dim villages, small campfires, and a green planet with no clear signs of industry. If they're 10,000 light years away, they would see Earth from the Stone Age, when our ancestors hadn't yet invented the wheel. And if they're 100,000 light years away, they would see no humans at all. They would see herds of wild animals, pristine forests, and a planet that never knew intelligence. Information always arrives late. Observation is always a look into the past, and that past causes every civilization to misunderstand each other. You think they know we're intelligent. No, they only see the version of Earth from the era when the light signal just reached them. They think we're sending invitations? No. The radio signals we sent 50 years ago, arriving where they stand today, may be just whispers lost in noise. They think we're ready to meet? No. They have no idea we exist in their present moment. And here's the great paradox. Any civilization far enough away to be interesting to us sees an Earth no longer suitable for meeting. By the time our signal arrives, we've changed. By the time their signal arrives, they've changed. There is no synchronization, no perfect moment, no way for an invitation across 10,000 light years to arrive at the right time, to the right people, to the right civilization. And if they don't know we exist, or only know our ancient version, why would they come here? Why would they expend star-level resources just to visit a planet they see as a pristine wilderness? Information isn't just delayed, it's obsolete the moment it leaves its source. This is the ultimate verdict the universe imposes on all. Every civilization lives in its own information bubble, separated by signal travel time. We don't know them, they don't know us. But the information verdict still hasn't told the whole story. If you think them not knowing we exist is bad enough, wait until you hear about what astronomers call the cosmic haystack, a pile of hay so massive that the concept of finding the needle becomes overly optimistic. To make it easy to picture, imagine you drop a tiny needle into a haystack. Hard to find, sure, but at least you know which haystack it's in. In the universe, you don't just not know where the needle is. You don't even know which haystack contains it, or whether a needle exists in the first place. The problem of finding extraterrestrial signals is the same. Our galaxy has about 200 to 400 billion stars. Each star might have a few planets. Some planets might lie in the habitable zone. Some civilizations might have existed. Some might have broadcast signals. But the question is, are we listening in the right direction, at the right time, on the right frequency, from the right civilization, or not? And the answer is almost always no. Let's break down the three necessary conditions for one civilization to detect another via radio signals. Right time, right direction, right type of signal. First, right time. As mentioned earlier, our signals have only spread about 120 light years so far. If a civilization 500 light years away is scanning the sky right now, they hear nothing. Not because we aren't talking, but because the signal hasn't arrived yet. Conversely, if they broadcast a signal 1,000 years ago, it would only reach Earth in the year 3024, a millennium after our current moment. Two civilizations must broadcast at the right moment, in the right historical phase, during the right technological era, to have any chance of catching each other. But when the average lifespan of a civilization might be only a few thousand years, and signals take thousands to hundreds of thousands of years to travel, this chance is like two people at opposite ends of Earth throwing bottles into the ocean at the same time and hoping they collide in the middle of the Pacific. The probability is near zero. Second, right direction. This is the part most people don't think about. Radio waves don't spread evenly in all directions with equal strength. Most human signals are beamed downward toward the ground, not upward into space. Radio stations, TV broadcasts, radars, all focus energy in specific directions. The leakage into space is tiny and weak. For a civilization to detect a signal from Earth, they would need to be looking exactly at Earth's position during the brief window when the signal is directed toward them. A small error of a few degrees in the sky is enough for them to hear nothing. Even powerful directed signals, like the 1974 Arecibo message, were focused into a very narrow beam. If the civilization isn't inside that radio laser cone, they never know the signal existed. Third, right civilization. This is the cruelest condition. Suppose there are 1,000 civilizations in the galaxy. Sounds like a lot, but compared to 400 billion stars, it's an absolutely tiny number. The odds of two civilizations being within 120 light years of each other, the distance our signals can reach, are like dropping 2 grains of sand into the Sahara Desert and hoping they land a few millimeters apart. That probability is so small, you almost have to call it a miracle. The cosmic haystack isn't just a metaphor. It's mathematical reality. There are thousands of different dimensions in the search space for signals. You have to be right on frequency, right on time, right on direction, right on signal type, right on range, right on civilization. If even one factor is wrong, you hear silence. Not because no one is out there, but because the universe is extremely good at making civilizations invisible to each other. And the beautiful yet bitterly ironic part of this story is the silence of the universe doesn't mean we're alone. It just means we're surrounded by a haystack bigger than the galaxy itself. And the needle, if it exists, is somewhere in the dark. But until the laws of physics change, or the universe suddenly decides to press the reduce information delay button, that needle will remain forever out of our reach. And even if some civilization is lucky enough to get through the cosmic haystack, looking in the right direction, at the right time, on the right frequency, at the right civilization, and finally discovers that Earth has intelligent life, a probability near zero, the next part is even more disappointing. They still won't come here. This may sound cold, but when you consider the social, technical, and energy constraints any civilization faces, you'll see that visiting Earth isn't just difficult. It's completely pointless for them. Start from the social perspective. A civilization advanced enough to detect Earth from hundreds or thousands of light years away has surely reached high stability. They may no longer have wars, no longer need territorial expansion, and no longer think in terms of conquering like in movies. Once you have technology to harness the energy of a star, resources are no longer an issue. Therefore, there's no economic reason to cross thousands of light years just for metals, water, or carbon, things they can get right in their own star system. If they've developed long enough to value knowledge, scientific knowledge can also be gathered remotely through observation. They could analyze Earth's atmosphere and know we have oxygen, water, methane, even signs of industry. No need to come here to check. In other words, no social benefit justifies the trip. On the technical side, suppose they're advanced enough to build ships that can travel near light speed. The journey to Earth still takes hundreds or thousands of years. During that time, mechanical systems degrade, materials fatigue, probes fail, and any small technical glitch could doom the entire mission. No material is immortal. No technology is zero degradation. No robot or AI can perfectly self-maintain every detail across millennia. An advanced civilization would look at this technical equation and say, no, too much risk. You might think, what if they just send small robots? But robots still obey the same energy limits, speed of light limits, radiation, cosmic dust collisions, all the things we just analyzed. And if they want a robot to arrive in 10,000 years just to send back a photo of Earth, they still face the final problem. The return information also takes 10,000 years to get back. No civilization launches a project spanning dozens of millennia without knowing when or if the results will arrive and whether they'll still be relevant. The energy equation is just as ruthless, whether they're type 2 or even type 3, expending a huge portion of stellar energy to send a ship to visit a distant planet, one they only see images of from thousands of years ago, is an unjustifiable decision. The trip consumes enormous energy, lasts extremely long, has a high failure rate, and upon arrival, there's no guarantee Earth still has life or that our civilization still exists. Imagine you want to visit a village you saw in images from 10,000 years ago. You don't know if it still exists or has turned into desert. Would you dare travel thousands of years just to check? That's exactly the situation every civilization faces. When you understand this, you see something very important. The universe doesn't just make meeting difficult. It makes meeting have no rational motivation, no economic reason, no scientific reason, no social reason, no technical reason, no informational reason, and no advanced civilization does something meaningless when they could use that energy and time to improve their own lives, build massive structures in their star system, or pursue projects far more meaningful than sending a ship into the void. That's why, even if they know about us, even if they detect our signals, even if they're curious, they still won't come. Not because they're benevolent, not because they're malevolent, but because the universe doesn't support that trip in any way. After walking through the 5 great verdicts of the universe, distance, time, energy, biology, and information, we can finally smile gently when we return to the most talked about story. UFOs, those blurry, shaky videos with bright dots jumping across the screen as if filmed by a mosquito on coffee. There's nothing wrong with people being curious, but it's amusing to think those blurry objects are often labeled interstellar alien spacecraft. By now, you and I both know one thing. If a civilization could overcome the 5 verdicts of the universe, they certainly wouldn't appear as faint glowing dots on someone's trembling phone camera. Let's analyze gently, in the simple physics style I love. When looking at UFO videos, the first question you should ask isn't, is it aliens? But what is the camera doing? In almost every UFO video, the fast flight, sudden direction changes, unimaginable acceleration, phenomena completely disappear once you stabilize the frame. Just lock the camera motion, and you'll see that most UFOs zipping across the sky are actually airplanes, birds, insects, or light reflections, all of which become supernatural only because the camera shakes. A real object traveling at interstellar speeds, say 0.1 C or higher, wouldn't appear as a faint glowing dot. It would create an ionization trail, a super hot plasma streak from radiation and air interaction. It would generate a destructive shock wave the moment it hits the atmosphere. It wouldn't hover quietly like a drone that lost GPS. And even if they use some technology to reduce physical impact, appearing in front of a low-resolution, shaky digitally zoomed phone camera is completely absurd. You can't ride light and then be defeated by an old iPhone camera. Next, let's talk size. In many videos, the bright object occupies only a few pixels, meaning you have no information about size, distance, speed, or shape. A 10 centimeters object at 5 meters can look identical to a 10 meters object at 5 kilometers. That's why UFO videos are always mysterious. You don't know what you're looking at. But mystery doesn't mean supernatural. Mystery just means insufficient data. A shaky camera and reflected light don't suddenly turn into an interstellar ship. Add the shaking. If you hold a phone and try to film a fast-moving object, you'll see it jerk, change direction, disappear, reappear. That's due to rolling shutter, a technical artifact in camera sensors that compresses, stretches, breaks, or distorts fast-moving objects. It's like looking through a vibrating shutter. The object isn't actually moving strangely. The camera makes you think it is. A real object with technology that breaks the universe's limits wouldn't need to jerk around like a glitchy slow-motion video. It would have smooth, stable, clear motion, not zip across the screen and vanish like a fly. Now imagine a civilization that breaks the speed of light, crosses thousands of light years, withstands cosmic radiation, defeats the rocket equation, sustains biology or AI across millennia. And after all that, when they finally reach Earth, what they do is hover in front of Navy pilots and turn themselves into a white streak on infrared camera. No, if they came here, you'd know. No shaky video needed. No strange glowing dot. They would appear clearly, or they would remain completely hidden with technology beyond our understanding. And more importantly, if they're advanced enough to make the trip, they're certainly advanced enough not to be filmed on 480p cameras. One more point, energy. Every report of objects accelerating from 0 to 15,000 miles per hour in 1 second violates the simplest laws of Newton. To accelerate a massive object to that speed in such a short time, you'd need forces so great the object itself would be destroyed, let alone any pilot or equipment inside. An interstellar ship wouldn't change direction like a fly. It has to obey the same dynamics as every other object in space. And if they have technology to nullify inertia, then you think that technology would manifest as a dancing light streak in a video. When you look closely, UFO videos don't show you alien technology. They show you the limits of cameras, the limits of perception, and the limits of interpreting data without enough information. But they don't show you physics, because if you apply physics to any UFO video, all the anomalous motions disappear once you account for shaking, camera angle, distance, rolling shutter, wind, and light reflections. UFOs in videos don't violate physics. They violate camera resolution. So when someone sees a glowing dot and says, "That's aliens," I just smile, not mocking, not condescending. Just the smile of someone who understands the universe is too strict for an interstellar ship to appear as a blurry object in a shaky handheld video. If aliens really came here, trust me, they wouldn't let you film them with a trembling camera, afraid of low zoom. But let's play an interesting intellectual game, because I know what you're thinking after all these verdicts we've gone through. What if aliens could come here? Then what would the physics of the universe have to look like? This is when we step into counterfactual thinking, not to challenge what physics teaches us, but to prove once again that if aliens really visited Earth, the entire physical structure of the universe would have to be rewritten from scratch. Let's assume, generously, that there's a civilization out there that breaks all 5 verdicts of the universe. They overcome distance by going faster than light. They overcome time by ignoring delay. They overcome energy by creating infinite sources. They overcome biology by being immune to radiation and gravity. And they overcome information by instantaneously knowing the entire galaxy. Sounds more like mythology than physics. But suppose all of it is real. What physics would have to exist for them to do that? First, breaking the speed of light. If they do this, Einstein's entire theory of relativity, the foundation of modern physics, collapses. Space-time would no longer be stable. Causal structure would break, leading to paradoxes like grandfather effects, where causes can occur after effects. The universe would allow meaningless time loops. Clocks would run backward. Events at one point could influence the past backward. If any of this happened, we would have observed it. But we've never observed anything like it. That means breaking the speed of light cannot happen. Next, to travel between stars without infinite energy, they would need an energy source unbound by the law of conservation of energy, a law never violated in hundreds of years of experiments. Even virtual particles, the Casimir effect or cosmic expansion, provide no mechanism for extracting free energy in a fantasy sense. The physical structure tied to energy is foundational to everything from fundamental particles to galaxies. To break it, you'd have to build a new universe. Then comes biology. To overcome radiation, you'd need materials with no ionizing interactions, meaning you'd have to redefine electromagnetic interactions. To overcome high-speed cosmic dust collisions, you'd have to redefine weak and strong nuclear interactions too. To travel thousands of years without mechanical degradation, you'd have to overcome entropy. the second law of thermodynamics, which all statistical physics rests on. Next is instantaneous information. To know the entire galaxy instantly, they'd have to break quantum mechanics' no communication theorem, the state discrimination theorem, and the information transmission speed limit established by decades of Bell experiments. All of this cannot be broken without collapsing the entire quantum theory, the most successful science in human history, accurate to 10 decimal places in predictions. Finally, to get through the cosmic haystack and know precisely we exist, they'd need to see through time, bypassing the observational limits of light speed, meaning they'd have to stand outside space-time. And if something exists outside space-time, it's no longer a civilization, it's a deity. And physics doesn't work with deities. When you gather all these conditions, breaking light speed, breaking energy conservation, breaking causality, breaking fundamental interactions, breaking entropy, breaking quantum theorems, breaking information limits, you realize the most important thing for aliens to come to Earth, the way UFO believers imagine. The universe would have to be a completely different universe from the one we live in. Not an upgrade to physics, not more advanced technology, but different physics with entirely new laws, unrelated to the ones we verify every day in particle experiments. GPS, nuclear reactions, electronics, astronomical observations. A universe like that would have no stable galaxies, no stable planets, no stable atoms. In other words, it couldn't support life in the first place. And this is the conclusion counterfactual thinking brings us back to. If aliens could come here, physics wouldn't be the physics we know, but the physics we know is the only physics that allows life to exist. Therefore, the very existence of aliens proves they cannot come here. A beautiful, tidy, inescapable paradox. But in reality, when you look at all of this, the 5 verdicts of the universe, those seemingly merciless limits, the doors slamming shut without a single apology, you might feel a little disappointed. So, we'll never meet anyone out there. But this is the moment I want to tell you something I believe more deeply than anything in physics. The universe isn't disappointing. It's just honest. The impossibility we've just painted isn't a tragedy. It's a mirror reflecting the laws that make the universe stable, that maintain its structure, and most importantly, that allow life, including you and me, to exist. If the speed of light weren't a limit, if energy didn't obey rules, if information could travel instantly, if entropy could be reversed, if fundamental laws could be bent at will, then the universe would have no stars, no planets, no stable atoms, no organic molecules, no evolutionary processes, no biology, no intelligence, no music, no stories, no one to ask the question, are we alone? The universe isn't preventing us from meeting aliens. The universe is simply operating in the only way that life can emerge. And when you look in that direction, you realize that the impossibility isn't a barrier. It's the most beautiful gift. It says that the universe operates according to profound, simple, unified, and unchanging principles. Those principles take us from quarks to atoms, from atoms to molecules, from molecules to cells, from cells to life, and finally to beings capable of sitting here, thinking about the very laws that gave birth to them. When you understand that the speed of light is the ceiling of the universe, you don't feel disappointed. You smile, because that very ceiling keeps everything from collapsing. When you understand that energy is never free, you don't get frustrated. You know that balance keeps stars shining steadily for billions of years. When you understand that information cannot travel instantly, you don't feel sad. You realize that the very delay creates a universe with clear causal structure, where the past creates the present, and the present creates the future. I've always believed that the greatest joy of science isn't in the things we hope are true, but in the things that actually are true. It's not about the universe bending to human wishes. It's about us growing mature enough to see the world as it really is, without exaggeration, without fanciful dreams, without imposing expectations. When you understand the universe exactly as it is, you don't feel sad about what's impossible. You feel beauty in what is possible. Beauty in consistency, beauty in clarity, beauty in the simplicity beneath the apparent complexity, beauty in every law, every constant, every limit connecting to one another like a perfect piece of music. Aliens cannot come to Earth. That fact doesn't make the universe sadder. It makes the universe clearer. It forces us to stop waiting for something strange to appear in the sky and start looking at the beauty right in front of us. Stars operating in perfect rhythm, spectra telling us the chemical makeup of the cosmos, gravity holding galaxies in rotation, and the quiet laws of physics guiding every smallest particle. You don't need UFOs to make the universe wondrous. It's already wondrous in its own way, the way of truth. And for a physicist, there is no greater gift than that, because when you understand the truth, you don't feel alone in the universe. You feel you belong to it. When we accept that direct meeting is impossible, that doesn't mean the search for life beyond Earth stops. On the contrary, it becomes more interesting, more scientific, and more realistic, because the right question isn't, when will they come visit us, but how should we look for them without violating the laws of physics? This is where SETI, search for extraterrestrial intelligence, comes in. Not with spaceships, not with warp drives, but by listening. Because even if civilizations cannot travel to each other, they may unintentionally leak technological traces through radio waves, lasers, or narrow frequency signals. SETI operates on a simple but profound principle. If you have technology, you create noise. Radar, television, satellites, navigation, military communications, all of them broadcast into space. In the past 100 years, Earth has created a radio bubble, expanding 120 light years, and though faint, it is a technological signature that could be detected by a sufficiently sensitive civilization. SETI isn't looking for ships, it's looking for signals, not for strange glowing dots. It's looking for ordered patterns that nature cannot produce. And this is where the concept of techno-signatures, one of the most serious research directions in modern astronomy, comes in. A techno-signature could be a narrow-band radio signal, an ultra-short laser pulse, unusual thermal structures around a star, or light patterns that no natural process can explain. The most famous example is the WOW signal of 1977, a strong 72-second radio burst that remains unexplained, never repeated, and to this day is one of the most intriguing techno-signature candidates. But that's just one small piece in a much larger picture. If a civilization develops enough to alter its star's environment, we could detect it through infrared data. If they build megastructures like Dyson spheres or Dyson swarms, we could detect them through missing light at certain wavelengths. If they harness energy on planetary or stellar scales, we could see industrial-like heat emission tails. That's why the Kardashev scale becomes useful. Type I controls planetary energy. Type 2 controls stellar energy. Type 3 controls galactic energy. A Type 2 civilization would leave observable traces, not by flying ships across our sky, but by distorting starlight. A Type 3 civilization would alter the thermal structure of an entire galaxy. Those are things we can search for with telescopes, spectrometers, all-sky infrared maps like WISE, or future surveys like the Roman Space Telescope. And the wonderful thing is, all these approaches are fully consistent with physics. No warp drive required, no negative energy, no breaking causality. They only require us to look at the universe with the eyes of a scientist, listening for faint signals in the noise, seeking order in chaos, and analyzing light like optical detectives. Even more practically, projects like Breakthrough Listen are collecting petabytes of radio data every year, listening to millions of stars across thousands of frequencies. Giant telescopes like the SKA will increase our sensitivity hundreds of times, allowing detection of weak signals like FM radio stations from hundreds of light years away. This isn't science fiction. This is physics. If we find aliens, the odds are high that we'll find their light before we find them. A laser pulse, a repeating radio signal, an anomalous heat signature, a strange dark streak blocking a star's light. The universe doesn't allow us to meet them directly, but it allows us to observe their traces, and perhaps that's an even more beautiful way. No need for them to land in a Walmart parking lot. No need for Hollywood battles, just light, the thing that has carried information across the cosmos for 13.8 billion years, telling us you are not the only one. And when we've talked about SETI, techno-signatures, and the realistic scientific paths to search for life beyond Earth, we finally return to the question humanity has carried for thousands of years. Are we alone in the universe? This isn't a question of physics. It's a question of the heart, of philosophy, of existence. And to answer it, we must accept two truths that seem contradictory, yet strangely harmonize. The first truth: the universe is too vast for us to be the only ones. When you look up at the night sky and see a few thousand stars, remember that's only 1/10,000,000th of the stars in our galaxy, and our galaxy is just one of trillions in the observable universe. Each galaxy contains hundreds of billions of star systems, and most star systems have planets. Among those planets, a significant fraction lie in zones where liquid water could exist. The universe isn't just big. It produces opportunities for life in numbers beyond imagination. In a universe like that, saying we are the only ones sounds like saying in the entire Sahara Desert there is exactly one grain of sand. Not very convincing. The second truth: every civilization lives in its own physical bubble. No matter how much life is out there, no matter how many civilizations, no matter how intelligent they are, each civilization can only see, hear, and understand the portion of the universe within its own information bubble, expanding at the speed of light. We have a radio bubble 120 light years wide. Another civilization might have one 500 light years wide. A younger civilization might have only 10 light years. Each civilization is like an island in a vast ocean, lighting its own lamp. But that light only reaches so far before darkness swallows it. No one sees anyone. No one hears anyone. No one touches anyone. The universe may be teeming with life, but the laws of physics, speed of light, energy, time, information, create invisible walls that prevent those islands from meeting. This is the most beautiful paradox of the universe. We are not alone in possibility. We are only isolated in physics. So the real answer to "are we alone?" is yes, but not in the way you think. We are alone not because no one else exists, but because the universe is structured in a way that prevents civilizations from intersecting. Not because we're special, not because we're abandoned, but because the laws of physics, the same laws that make life possible, are also the laws that prevent those lives from meeting. That isn't cruelty. That is balance. And that balance in itself is beautiful. When you step outside on a dark night and look up at the sky, you may feel that isolation, but you can also feel something else, an invisible connection. Because even though we cannot meet, we and every other civilization belong to the same set of laws, the same origin from the Big Bang, the same web of fundamental particles living in the same cosmic symphony. We cannot talk across thousands of light years, but we share the same physics, the same chemistry, the same stellar history that forged the elements of life. That makes us no longer lost. When you understand that, the question, "Are we alone?" becomes a different one. What are we a part of? And the answer is a vast, beautiful, unified universe where life can bloom in countless places. But each place is wrapped in its own physical bubble, like solitary, yet harmonious sparks in a dark ocean. Alone, perhaps, but also part of something far greater. And now, as we reach the end of this journey, from the first limits of distance, to the cruelty of time, to the unimaginable cost of energy, to the fragility of biology, and finally, to the silence of information, I want us to pause, take a deep breath, and look back at the whole picture. Not to feel disappointed, but to marvel. Because if there's anything I hope you carry away from this conversation, it's the feeling that the universe isn't beautiful because it grants what we want. It's beautiful because it's honest about what it is. The first verdict, distance, reminds us that the universe wasn't built to human scale. It's vast enough to collapse all our intuition, and that very vastness creates room for billions of galaxies, hundreds of billions of star systems, countless planets, and uncountable opportunities for life. If stars were closer together, if distances were smaller, the universe would be chaotic and unstable. The second verdict, time shows that every life, every civilization is just a small candle in a 13.8-billion-year canvas. And that isn't sad. It reminds us to cherish the moment we get to live, to think, to understand. The third verdict, energy, teaches us there's no physical magic for interstellar travel, but that very limit keeps stars burning steadily for billions of years, creating perfect conditions for life to evolve. The fourth verdict, biology, reminds us we are fragile yet wonderful products of this planet, of its pressure, temperature, magnetic field, chemistry that Earth provides. No creature is wrong for not being able to travel interstellar. We're simply right for the environment that created us. And the fifth verdict, information emphasizes that the universe wasn't designed for civilizations to chat easily. But information is exactly what lets us understand starlight, write equations, discover gravity, and for the first time in history, understand the nature of this very isolation. When you look deeply enough, you see that these 5 verdicts aren't prisons. They are the bricks that build the universe. They are why everything works. They are the foundation for every beauty the human eye has ever seen when looking at the night sky. The idea that the universe must conform to our desires, that it must allow interstellar travel, that aliens must visit, is a childish expectation. But when we mature scientifically, we learn something deeper. Understanding the universe exactly as it is beautiful enough. We don't need UFOs to make it wondrous. We don't need aliens to make it mysterious. We don't need faster-than-light stories to make it magnificent. The universe is already magnificent with truth. When you look at the light of a star and know it left there hundreds of years ago to reach your eyes today, that's magic. When you understand that every atom in your body was once forged in the furnace of an exploding star, that's magic. When you realize that simple laws can describe every motion from an electron to a spiral galaxy, that's magic. No one needs to knock on Earth's door to make the universe special. It already is. And this is what I want to tell you. In the style I've always believed, when you understand something deeply, truly understand it, then it is more beautiful than any wonder you could imagine. Truth doesn't break the beauty of the world. Truth is the beauty of the world. So if you ask me whether I'm sad that aliens will never come to Earth, I'll say no, I'm not sad. I know we're living in a consistent, logical, proud universe with its own laws, and that human intelligence is refined enough to read the lines the universe has written. And that alone means we're never truly alone. Thank you for joining me on this adventure. Keep asking questions, keep doubting, keep loving what the universe reveals, because in the end, it's not aliens that make the universe wondrous. It's your curiosity that does. If you want to keep exploring the beautiful mysteries of the universe with me, don't forget to subscribe so you don't miss any journey. See you in the next adventure, where science once again opens up new wonders.